which can be used when all else fails. You can't do anything algebraic. I could make a table, that type of thing, but this is another approach. It's a more graphical approach. It says that if f of x is less than g of x, which is less than h of x, in other words, g of x is in between two other functions, then their limits will also be in that same order. Well, that makes sense if the y values are in between each other in that order, smallest, middle, top, then we can squeeze the limits together as well. So my example for this is also going to be one of the big limits that is you should memorize. I mean, I'm going to star this. It's going to come up so often, and it's so important. And this squeeze theorem is the best one to use to prove this limit. So here we go. The limit as x approaches 0 of sine x over x. Okay, so I know right now that if I plug in 0, I get 0 over 0. And I can't do anything mathy. So I want to look at the graph of this and play around and see if we can squeeze or sandwich sine x between two other functions. Okay? So I'm going to go to Desmos, and I'm going to type in y equals sine x divided by x. And you'll notice our graph here. If you could see the whole thing. Let's see if I can get the whole thing in there. There we go. It's kind of an interesting little graph. If I go to the table, which I'm going to put here, it is undefined at x equals 0. And we can kind of make a guess of where it's going to go. It looks like it's heading to 1. But what I'm going to do is I'm going to use the squeeze theorem. So what I think I'm going to do is I think it's approaching 1 here. I'm going to squeeze this graph between two other graphs. So I'm going to go down here and do, let's just be fun and do x squared plus 1. Well, that's above it, isn't it? Or equal to it, yeah. And I want to squeeze that between another graph. So I'm going to do the other one as negative x squared. I want it to be closer. We're squeezing it. Plus 1. Is the graph of sine x over x sandwiched between these two parabolas? It is. So that means that, so this was on the bottom, negative x squared plus 1 and x squared plus 1. Sine x over x can be sandwiched between these two graphs. That also means that the limits are also sandwiched in that order. So the limit as x approaches 0 of negative x squared plus 1 is going to be less than or equal to the limit as x approaches 0 of sine x over x, which is going to be less than or equal to the limit as x approaches 0 of x squared plus 1. Now, the reason I picked nice parabolas is because I know I can do direct substitution. That's pretty easy. So when I substitute in 0 for x, I'm going to get a 1 here. This is what we're trying to find. And over here, when I substitute in 0 for x, I get a 1. So that means that the limit as x approaches 0 of sine x over x is in between 1 and 1. Well, that means it's 1. And we'll use therefore. If you've never seen that symbol, that means therefore. Because we just proved that limit is true forever and ever and ever. This is one that is super important to know. And we can play with this limit and come up with some other lovely other limits. So what if I had the limit as x approaches 0 of sine of 3x over 3x? Well, let's look and see what that graph looks like. How similar is that? Let's go back here. Y equals sine of 3x divided by 3x. Well, it looks like we've got some more like waves out to the side, but it still looks like it's going to 1, and guess what? It is. So as long as this angle and the denominator are the same, it's going to go to 1. So I don't care if it was the limit as x approaches 0 of sine of a happy face over a happy face, it's going to be 1. But what if I had sine of 3x, but this was just an x? All right, so we're going to do some algebra things. Algebra things? Yes. Okay. I'd really like this denominator to be a 3x. So I need to put a 3 down there. But I can't just multiply the denominator by 3. I'd have to multiply the numerator by 3 as well. That's good math. So 3 and 3. I'm going to multiply the top by 3 and the denominator by 3. Now, do you remember when we talked about the rules of limits, that if I have something times a function, so I'm going to kind of separate out the function I want just this, right? Sine of 3x over 3x. I can kind of factor out that 3 now, and it's going to go on the outside of the limit as x approaches 0 of sine of 3x over 3x. So I kind of factored that out. This reduces to 1. And then we have the 3 on the outside, so that just gives me 3 times 1, which is 3. What do you think would happen if I had, let's see, sine of 2x over 3x? Well, I don't want the 3 there. I want the 2 to be there. So what I'm going to do is, that's kind of like taking a third of something. 1/3 is dividing by 3. So I'm going to factor that kind of out. Or, factor it out kind of. Unmultiply it. That's still the same thing. They're still equivalent. Now I want that denominator to have a 2x, so if I multiply this by 2, I have to multiply the numerator, but I'm going to do that right here. So now this 2/3 can go on the outside, and then I have the limit as x approaches 0 of sine of 2x over 2x, which all of that just reduces to a 1, so I end up with 2/3. So I've had people ask me, so is there a little shortcut there? Coefficient, 3, 1, 3, 3, 3. Yes, there is a shortcut. Now I'm going to use this again to prove another super important limit that's worth your time to memorize. And it's the limit as x approaches 0 of 1 minus cosine x over x. Now, I could use a table, I could use a graph, but for our purposes here, we're going to do something mathy. So what I want to do is I am going to have some math fun. I'm going to multiply this fraction by another fraction. I'm going to multiply it by 1 plus cosine x, kind of the conjugate. Because by the way, right now if I plugged in a 0 and get 0, that would be a 1, 1 minus 1, not good. So I'm going to multiply the numerator and the denominator by the same thing. So when I multiply that numerator together, I'm going to get 1 times 1 is 1 plus cosine x minus cosine x minus cosine squared over, now if you remember what I talked about when we were doing the conjugates earlier, don't distribute the denominator, it's not worth it. Cosine x minus cosine x are going to subtract out. And then I have the limit as x approaches 0 of 1 minus cosine squared over x times 1 plus cosine x. Now, for those of you who remember your pre-cal, 1 minus cosine squared is sine squared. Ooh, okay, so now I've got sine squared, which is really sine times sine. And these are being multiplied, so that's an x times a 1 plus cosine x. Well, look at this sine x over x. What's going to happen as x approaches 0? Well, that's just going to go to 1, right? So I'm going to separate this out. Remember, we can do this because of the rules of limits. This is going to reduce to 1. Here. This is just a 1. Now I'm going to let x go to 0. I'm going to actually plug in 0 for x. So I'd have sine of 0 over 1 plus cosine of 0. And cosine of 0 is 1. And sine of 0 is 0. So I have 0 over 1 plus 1. That is 0. So this is another super important limit. It will come up a lot. And it's worth memorizing. Whoops.